Right. So I'd like you to know that these are the three equations, general equations for representing nuclear reactions. Now we know that chemical reactions are brought about by the exchange or the transfer of valence electrons. But nuclear reactions have to do with the nucleus or nuclei. Nuclei is the plural form of nucleus. Is that okay? All right. So these are the three general equations. This one is for alpha decay. So you notice that here alpha, of course, we could have written alpha like this, but because the helium atom has the same nature as the alpha particle, you can replace it with helium. So here is beta, but of course, you can replace it with electron because they have the same nature. And this one is gamma decay. This is beta decay. Is that okay? All right. Now, each atom that is involved in a nuclear reaction is called a nuclide. So this is how you represent a nuclide. You can use X or Y if the atom is not specified. Is that okay? So up here is A, down is Z. A represents the mass number. And we know that mass number is proton number plus neutron number. Hope you've not forgotten that. And Z, I like to cross my Z so it doesn't look like 2. Is that okay? So Z represents the proton number, which is also called atomic number. So proton number is the same as atomic number. Is that okay? All right. So that if you are given a particular nuclide, let's say sodium, we know that the mass number is 23 and the proton number or the atomic number is 11. And if you're asked to find the neutron number, of course, from this equation, from this formula, I know that neutron number will be equal to the mass number minus the proton number. And in this case, it will be 23 minus 11, which will give us 12. Is that okay? Now, if you know how to write this correctly, it becomes very clear that you can also write or represent the three subatomic particles correctly. And what are there? We have proton, we have neutron, and we have the electron. And you can as well represent the, excuse me, the three types of radiation. You remember that's alpha, beta, and gamma properly. So how do you represent the proton? So up here is the mass, and down here is the charge. So it has the mass of 1 and a charge of +1, or you just write 1. And remember that it has the same nature as hydrogen. So we also represent hydrogen the same way. That's the normal hydrogen, not the isotopes, deuterium and tritium, all right? Now for neutron has the same mass as proton, but it has no charge. So 0 will be down here. Electron has 0 mass and the charge is -1. Now, normally we regard the mass to be 0 because it is so infinitesimally small that you can actually regard it to be 0 when compared with that of proton. We know that the mass of proton is approximately 2,000 times the mass of electron. That is 1840 times actually. All right, so electron has 0 mass, the charge is -1. All right. Now, what about the alpha? Now, alpha has mass of 4 and the charge or the proton number is 2. All right. And of course, quickly, you just notice that it shares the same nature with the helium atom, which has 4 as its mass and 2 down here. Is that okay? Now, beta has mass of 0 and a charge of -1. So you quickly recognize that it has the same nature as this guy, the electron. Whereas gamma is 0, 0. Mass is 0 and the charge is 0. It has the nature of the electromagnetic wave, all right? Electromagnetic wave. Okay, so let's answer the question we have. A nuclide, this, emits an alpha and a beta particle. So let's write it down. We have 2O2 and we have 84. Okay, so this is the parent atom. The daughter atom, we can use X. What would be X if an alpha particle is emitted and a beta particle is also emitted? All right, so looking at this equation, the equation here, I know that the atomic number of the daughter atom will decrease if an alpha particle is emitted, whereas it will increase. Can you see here? It will increase if beta is emitted. But of course, if beta is emitted, the mass number remains the same. Okay, so here I have 4, I have 2, here I have 0, I have -1. Okay, now simply put, this is just like saying if I want to get the atomic number of the daughter element X, it will be 84 minus 2, which will give us 82. Then 82 minus -1, and minus is plus. So that will give us 83. 83. Okay. Now, if you want to be sure that you're correct, you say 83 plus 2, 85 minus 1 will give you 84. Can you see? The left-hand side must be equal to the sum of, okay, all that you have in the right-hand side. Is that okay? Okay, what about this one? The mass minus 4 minus 0 will give us 198. If you want to test to be sure that you're correct, you say 198 plus 4 will give you 202 plus 0, 202. Remember that the left-hand side must be equal to the right-hand side. Very important. Okay, so it's clear that the answer, so they are saying the atomic number of the resulting nuclide is what? So it is 83. That's option B. Now let's come over to question number 2. How many beta particle or particles are emitted in the radioactive decay? So let's put down 19879, and then we have 198 and 80. All right, I already know that the mass will not be affected, okay, if an electron or a beta particle is emitted. Is that okay? Can you see that the mass here is the same as the mass here? All right, so let me put down one electron or one beta particle. So this is 0 minus 1. So let's check. Of course, I know that the mass will remain the same, okay? And then the atomic number will have to increase. Remember, if beta particle is emitted, the proton number increases. But if alpha particle is emitted, the proton number decreases. That can help you a lot, all right? So 80 minus 1, will, of course, will give you 79. Hence, the equation will be balanced, all right? Okay, so can you see it's only one? So option A is the correct option. All right? All right, so this one is for you. We have radium 226. The proton number is 88. And we have polonium here, but we are told that 2 alpha particles, okay, were emitted. So alpha plus alpha. Here is 4, here is 2, 4, 2, okay? All right, again, what do I do? This minus 4 will give us 222 minus another 4 will give us 218. 218. And then this one, 88 minus 2 will give us what? 86 minus 2 will give us 84. So 84 here. All right. So the correct formula for the nuclide is this. That's D.